While examining the points of origin of the universe, numerous questions strike a chord. What came before the massive explosion? If there was no before the enormous explosion, long ago, the response appeared to come directly from heaven. Even Isaac Newton believed that the universe was created by God. Approximately 6,000 years later, researchers, including a young Albert Einstein, assumed the universe would last forever, unchanging and perpetual. Stars could form, planets could have an impact and move, and civilizations could rise and fall on a massive scale. It appeared that the universe was consistent. It was only after the 1930s that convincing evidence of the universe's expansion was demonstrated. By the 1960s, the idea of the universe beginning with the Big Bang gained widespread acceptance. This change in our understanding of the universe was as significant as the shift to a heliocentric solar system model. Despite this new viewpoint, it raised additional questions about what existed before. What was the nature of space at the Big Bang before it began to expand? And if everything must have a beginning or end, the well-known physicist Brian Cox investigated these profound questions. Cox provides a crucial perspective, hinting at the existence of the universe before the Big Bang, challenging traditional concepts of the cosmos's beginnings. He explains that, while the universe most likely began in a very hot and dense state, referred to as the Big Bang, it was not necessarily the absolute beginning. According to Cox, it is possible to discuss a before the Big Bang. His work has made complex scientific concepts more accessible to the general public. Investigation into the cosmic theory of inflation reaches back to the mid-20th century when observations of distant galaxies showed they were receding from us, a finding consistent with Einstein's general relativity. This recession pointed to an expanding universe, implying that in the distant past, everything was closer together. Time and light also shifted, cooling the universe. Through backward extrapolation, scientists discovered a condition in which the universe was so hot that atoms couldn't form. This led to the prediction of the cosmic microwave background, CMB, an afterglow of the Big Bang, discovered in 1964 by Arno Penzias and Robert Wilson. This discovery confirmed the Big Bang theory, suggesting the universe began from an extremely hot and dense state. But how far back can we extrapolate? At a state where matter and antimatter pairs formed suddenly, or where even protons and neutrons degraded into a quark-gluon plasma, these considerations lead to a different perspective on the universe's origin. Rather than a specific hot, dense state, the early universe might have undergone a period of astronomical inflation where space itself expanded rapidly. During this time, the stage was set for, but did not result in, the creation of a singularity. What happened before inflation, or whether inflation was timeless, remains an open question. It is clear, though, that the Big Bang was not a definitive start. So, if not the Big Bang, what was the origin? The short answer is that we don't know for certain, but there are intriguing possibilities. One theory holds that, prior to the Big Bang, the universe was an infinite stretch of dense, ultra-hot material governed by quantum mechanics. The Big Bang could mark the shift to a universe driven by classical physics. Stephen Hawking's no-boundary proposal suggests that, before the Big Bang, reality was finite but without boundaries, like the surface of the Earth. On the other hand, a scenario proposed by Brian Cox suggests that, before the Big Bang, there was no universe. Instead, there was a vast expanse of energy in a state of near quietude, gently oscillating. This energy triggered inflation, a rapid expansion, eventually converting into matter and leading to the universe we know. Cox's ideas challenged traditional creation stories, suggesting that inflation etched patterns into the universe, forming regions of varying density. Eventually, these dense regions collapsed to create the first galaxies and stars, ultimately resulting in our solar system. Cox is not alone in these views. Theoretical physics suggests that the universe may be part of a cycle of big bangs and big crunches, spanning time back and forth. This concept, based on string theory, asserts that the universe undergoes cycles of early expansion and contraction. Although various iterations of this model struggled to match observations, recent developments have refined the theory, suggesting that a cyclic universe may be possible. The cyclic model challenges conventional views that argue the universe is a singular process that never ends. This model also provides an alternative to the inflationary model, based on the idea of an infinite number of universes within a multiverse, as opposed to a periodic universe. The cyclic model suggests a more comprehensive explanation that does not necessitate multiple universes. A variant of this hypothesis is the Big Bounce model, where the universe expands and contracts in cycles. Some versions assert that this occurs once, while others claim it continues indefinitely. The Big Bounce model still requires significant advances in theory, but challenges the idea of a singular beginning. Critics of the inflationary theory argue that it is too complex and contrived, suggesting that a model like the Big Bounce might provide a simpler, more in-depth explanation. According to the cyclic universe model, time may reverse course in a mirror universe, possibly explaining dark matter and other cosmic phenomena without needing a complete theory of everything. The search for the origin of the universe continues, testing creative concepts in traditional cosmology and presenting novel insights into the true nature of the universe. Join us as we explore how Brian Cox has challenged the cosmic theory of inflation and made science accessible to the public, fostering participation in discussions on these profound questions. The idea of the Big Bang first became apparent in the 1920s and 1930s when astronomers observed that distant galaxies seemed to be receding from us. According to Einstein's general relativity, a universe that remained static would be gravitationally unstable. Everything would have to be moving toward or away from each other. These observations demonstrated that the universe was expanding. An expanding universe indicates that things were closer together in the distant past. This also implies that light in the universe changes in wavelength over time, cooling the universe as it ages. By extrapolating sufficiently far back, we reach a state where everything was so hot that neutral atoms couldn't form. If this is true, we ought to see an additional glow of radiation today, which was found in 1964 as the cosmic microwave background, CMB. This discovery confirmed the theory of cosmic inflation. Extending this back to a single, extremely hot, dense state suggests a point of singularity with infinite density, which present physics cannot accurately describe. Instead, Cox suggests that the initial universe was more than just a singularity, rather an evolving, complex state through processes not yet fully understood. His perspective challenges the idea that the Big Bang was a definitive beginning and suggests that the beginning we perceive could be part of a larger, ongoing cycle. Cox's views align with some aspects of the cyclic universe model, which posits that the universe undergoes multiple phases of expansion and contraction. Though still speculative, this model provides a framework within which the Big Bang could be just one event in a series of cosmic cycles. The idea of a cyclic universe suggests that each Big Bang may be followed by a significant crunch, leading to a new cycle of expansion. This contrasts with the conventional Big Bang theory, which holds that there is only one origin point for the universe. Exploring these concepts, Cox and other physicists delve into inquiries regarding the nature of time, space, and the fundamental forces of the universe. For instance, the idea of cosmic inflation, an explosive growth immediately following the Big Bang, has played a crucial role in describing the uniformity of the universe and the distribution of galaxies. However, the final nature of this inflationary period and how it affects the future of the universe remains a topic of extensive research. Theories such as quantum gravity and string theory provide new insights into the possible conditions that existed before the Big Bang. These theories attempt to reconcile general relativity and quantum mechanics, offering a more comprehensive understanding of the origins of the universe and its evolution. For instance, String theory suggests that the fundamental components that make up the universe are not point-like particles, but rather strings with only one dimension that vibrate at a variety of frequencies. In summary, whereas the Big Bang theory significantly advanced our understanding, it is not the final word on the universe's origins. Questions about what came before the Big Bang, the possibility of inflation, and the cyclic universe continue to drive scientific inquiry. The exploration of these inquiries tests the limits of our knowledge and challenges our understanding. The universe, through research, moves forward with new observations and theories that will continue to advance to help us better understand the universe's history and its ultimate destiny. The pursuit of a comprehensive theory of everything is one of the most enduring, profound, and exciting endeavors in modern science. New discoveries and fundamental insights into the pursuit of reality's nature and understanding the origins of the universe have captivated the imagination of humans for centuries. From myths evolving into stories that adhere to rigorous scientific investigation, the Big Bang Theory revolutionized our understanding in the 20th century. However, it left fundamental questions unanswered and brought up new ones about the truth and what came before. One of the most fascinating aspects of cosmology is the notion of time as a whole. The Big Bang suggests a starting point, a time when space and time as we know it developed out of a state with infinite density. However, theories that challenge this view propose that the universe is cyclical, where events grow and shrink in a pattern that is repeated. According to this cyclic model, time may not be linear, but rather a component of a larger cosmic rhythm, where each cycle of contraction follows an expansion, possibly triggering a new cycle of creation. In recent decades, advances in theoretical physics have provided new frameworks to investigate these concepts. For instance, string theory suggests that the universe is made up of tiny, vibrating strings of energy. These strings vibrate at various frequencies, resulting in the particles and forces that govern our universe. String theory also posits the existence of additional dimensions beyond the familiar three dimensions of space and a single temporal dimension, providing a possible explanation for where space and time themselves originate. Within string theory, the idea that brains, short for membranes, provide an additional route for comprehending the origins of the universe is significant. Brains, objects with a higher dimension, can interact and collide in ways that influence the course of the universe's evolution. In some versions of string theory, our universe is portrayed as a brain embedded in a space of a higher dimension, with interactions between brains giving rise to phenomena like inflationary bursts of growth. The idea of inflation, proposed in the 1980s, remains a cornerstone of modern cosmology. Inflation suggests that in the earliest moments, the universe underwent a rapid, exponential increase, expanding the space-time fabric from atomic to cosmic scales. This period of inflation would help explain the cosmic microwave background radiation observed today, as well as the galactic distribution across the universe. However, while inflation offers a compelling justification for these observed phenomena, the precise mechanism behind its origin remains a subject of ongoing debate and research. Some physicists have proposed variations of inflation, such as eternal inflation, which suggests that inflationary processes continue indefinitely, resulting in the creation of a number of pocket universes within a greater multiverse. For each pocket universe, there may be various physical constants and laws of physics providing a possible explanation for the fine-tuning of our very own universe for life. A multiverse, in which our universe is only one of many that could exist with diverse properties, challenges traditional notions of cosmic uniqueness and brings up philosophical concerns regarding the nature of reality and our place within it. If the multiverse exists, it could indicate that the circumstances for life, as we know them, are not unique to our universe, but rather the result of a cosmic lottery in which various universes produce distinct outcomes. Beyond theory, speculation, and observation, cosmology continues to provide new insights into the universe's history and structure. The discovery of dark energy in the late 1990s reshaped our knowledge of cosmic expansion, implying that the expansion of the universe is accelerating rather than slowing down, as was previously believed. Dark energy remains one of the greatest mysteries in physics, comprising roughly 70% of the universe's energy density while avoiding direct detection. Similarly, a type of matter known as dark matter, which interacts gravitationally but not electromagnetically, accounts for roughly 27% of the universe's energy density. Its existence is inferred from gravitational effects on galaxies and clusters of galaxies, but its precise nature remains unknown. Understanding dark matter is crucial, not only for deciphering the universe's structure on large scales, but also for evaluating the reliability of basic physical theories. Dark matter, along with ordinary matter and dark energy, shapes the universe, with less than 5% of the total energy density consisting of ordinary matter. The cosmic web of galaxies and galaxy clusters observed through telescopes provides information regarding the universe's evolution from its earliest moments, offering cosmic fossils that astronomers and cosmologists decode to understand the processes that control its development. Over the past few years, advancements in observational astronomy have led to groundbreaking discoveries, like gravitational waves, ripples in spacetime caused by major cosmic events, such as black hole collisions. The detection of gravitational waves in 2015 confirmed an assertion made by Albert Einstein a century prior in his general theory of relativity, opening a brand new doorway into the study of the universe's most extreme phenomena, gravitational. Wave astronomy promises to reveal insights into the nature of black holes, neutron stars, and other exotic objects that defy conventional comprehension. Through observation, scientists can study these cosmic collisions, test gravity theories under extreme conditions, and investigate the basic properties of spacetime itself. Meanwhile, experiments at particle accelerators, such as the Large Hadron Collider, LHC, seek to recreate conditions similar to those just after the Big Bang by smashing protons together at nearly the speed of light. Physicists aim to unlock the early universe's secrets and investigate the primary forces and particles that govern its behavior. These experiments provide concrete evidence that complements theoretical models, offering insights into the fundamental building blocks of the universe and how they interact. One of the many unsolved mysteries in cosmology is the ultimate fate of the universe. In accordance with its density and the nature of dark energy, the universe may continue expanding indefinitely, eventually turning cold and pitch black in a scenario called the heat death or big freeze. Alternatively, if dark energy behaves differently, or if the universe contains sufficient matter to reverse expansion, a significant collapse may occur, causing the universe to revert to a hot, dense state reminiscent of the Big Bang. The possibility of a universe in which phases of expansion and contraction continue indefinitely provides a different viewpoint on cosmic destiny. In such a scenario, each cycle may lead to the formation of new galaxies, stars, and conceivably life, sustaining a cosmic drama on scales of time and space beyond human comprehension. As our understanding of the universe evolves, so too does our appreciation of its profound mysteries and beauty. From the smallest subatomic particles to the largest cosmic structures, the universe continues to expand and test our imaginations. The search for a complete theory of everything, a consensus that makes sense of both quantum mechanics and general relativity, remains a central goal of modern physics, promising to expose the fundamental principles that control the universe and our existence within it. In conclusion, the exploration of the universe's beginning and end is one of humanity's greatest intellectual endeavors. Through theory, speculation, observation, discovery, and experimental verification, scientists seek to unravel the cosmic fabric that has come together over billions of years. Each new observation and theoretical breakthrough brings us one step closer to comprehending the nature of reality itself, pushing the boundaries of human knowledge and inspiring future generations.